Okay, good. Hi, everyone. Welcome to this live stream by Streamkap. By way of a quick introduction, Streamkap is a streaming ETL platform. And today we're going to be joined by Marcin, a staff data engineer at Spoton. Spoton is a leading provider of point-of-sale systems. It is used worldwide by thousands of restaurants and retailers. And it's probably likely that we've all interacted in somehow with a spot-on system at our restaurants and shops at some point. Spot-on have been a customer for a while now and has seen great success with Snowflake and Streamkap. And I'm looking forward to us all learning more about how that journey went. What we'll be doing today is a approximately 15-minute presentation by Marcin, followed by Q&A, and we'll use your questions for that. So on that note, over to you, Marcin. So welcome, thanks for joining us. How are you doing today?
Thank you, Ricky. So let's start.
Okay.
Imagine relying on outdated data for crucial decisions. How confident would you feel? This is the reality many have to face with traditional data pipelines and stale models. Hello, my name is Marcin Migda. I'm data engineer at Spoton, and besides building data pipelines, I also enjoy building Lego and playing complex board games. After today's presentation, you will learn how dynamic tables solved a real human problem and how data can impact real people and businesses. But first, let me tell you about Spoton. We are a 2,600-person USA-based company specializing in point-of-sale systems and payment processing software and hardware for restaurants and retail. We proudly serve over 30,000 customers. When I joined Spoton, there was already a well-established reporting data pipeline in place. However, as you will see, even established systems can have significant gaps. Here are some key metrics. The data sync time was averaging about 5 minutes. The model refresh time added another 15 minutes, and the total delay from data capture to actionable insights was approximately 20 minutes. While this may seem efficient, in the fast-paced environment of our clients' businesses, even 20-minute delay may become a source of frustration. One day, a business approached me with a pressing issue. Many of our clients' restaurants relied heavily on accurate and timely data to function smoothly, particularly when it came to managing tips for their staff. However, managers complained that employees had to wait 20 minutes before they received their share of the day's tips. The wait staff were getting frustrated. They had to wait about 20 minutes at the end of their shifts before receiving their share of the day's tips. This delay was causing a lot of discontent among the staff, as they were eager to wrap up their day and head home. Not only were the waitstaff annoyed, but the restaurant manager was also facing the heat. The delays in tip distribution were creating unnecessary friction and inefficiency at closing time. Determined to find a solution, I started exploring various tools. One option was teams and tasks in Snowflake, which were complex and not easy to maintain. The other option was Spark, which is a powerful tool for data processing. However, our company didn't have the ready-to-use infrastructure to implement Spark quickly and efficiently. This led me to search for alternative solutions that could seamlessly integrate with our existing systems. Eventually, I discovered dynamic tables from Snowflake, a relatively new solution on the market. Dynamic tables offered a way to process data in a simple and effective way, significantly reducing the delay we were experiencing. The implementation of dynamic tables turned out to be a game changer for us. It provided the speed and reliability we needed. Now let's take a closer look at how our system used to work. Our previous setup relied on batch processing, which meant that data synchronization and updates were handled in intervals rather than in real time. This created significant delays, especially during peak operational times. Here's a diagram of our previous data pipeline. The process involved several stages, each adding to the overall latency. Data changes were captured by Fivetran using change data capture, but loaded into Snowflake in batches. In Snowflake, we were using incremental tables refreshed by dbt on a schedule set by Fivetran. Finally, insights were generated and made available to end users. The total delay from data capture to actionable insights was around 20 minutes, as shown in our key metrics. This pipeline, while functional, was not sufficient for the real-time needs of our clients. To remind you of the key metrics, our data sync time was averaging about 5 minutes. The model refresh time added another 15 minutes, resulting in a total delay of about 20 minutes. These metrics highlighted the need for a more efficient solution to reduce the overall latency. To fix the first problem, with help came Streamkap. Streamkap is a streaming platform that replaced Fivetran in our data flow. Its main responsibility remained the same, to sync data to Snowflake. However, Streamkap does it better, but by utilizing Snowpipe Streaming for near real-time updates instead of batch inserts. Here are the updated key metrics after we implemented Streamkap. Our data sync time dropped dramatically from 5 minutes to under 5 seconds. Most of the time, it is even sub-second latency. This change alone significantly improved our overall data pipeline performance, but we still need to face second problem related to model refresh time. Before we go further, we need to answer an important question in the context of this presentation. So, what are dynamic tables? Dynamic tables offer declarative transformation, which means instead of specifying how to perform the transformation, you simply tell them what you want. This makes the process much more intuitive and efficient. You just provide expected result as SQL. They empower automated data refresh. Dynamic tables ensure that your data is always fresh and ready to use, eliminating the need to schedule refreshes. And also, they are built for data pipelines. You can seamlessly integrate dynamic tables into your workflow for smooth automated data processing, simplifying the entire data engineering process. In essence, dynamic tables simplify data engineering by providing automated and reliable data transformation pipelines in Snowflake. Okay, so to leverage dynamic tables, you need to meet certain requirements in your dbt setup. And as you can see, that's it. That's the only dbt dependency you need. I recommend to use library inversion at least equal or higher to 1.6 because of breaking syntax changes in previous versions. So now let's answer the question, how to create dynamic table. So creating dynamic tables in Snowflake with dbt is a streamlined process. You define your transformation logic declaratively and configure the model with few key variables. The materialized parameter is set to dynamic table, indicating a Snowflake dynamic table. Additionally, two required parameters are essential. Snowflake warehouse. This parameter specifies the Snowflake warehouse responsible for automatically refreshing the dynamic table. And the target lag. This parameter defines the desired latency between data changes and the update reflected in the dynamic table. Snowflake will strive to keep the table data within this lag window. However, factors like SQL complexity, warehouse workload, and data volume can influence the actual refresh time. This approach offers significant advantages compared to traditional dbt models. Dynamic tables enable near real-time data availability, minimizing the delay between data capture and actionable insights. A very big advantage we gain with Streamkap is that CDC events are also inserted into our warehouse. However, this contains every change that has occurred to our data. However, in our reports, we are usually interested in the latest state of the table. There is ready-to-use SQL, which can be found in Streamkap documentation, but don't worry, this can be simplified to single parameterized macro. A very big so as you can see, you can have very generic macro with just a few parameters to make it simple. If we have existing pipeline that relies on incremental models, there are few steps to follow to convert them into dynamic tables. First one, update the model config to reflect the new setup. Second one, set the materialized parameter to dynamic table. This tells DBT to treat the model as dynamic table. You need to set the target lag and Snowflake warehouse parameters to configure the refresh settings. Then you remove any if is incremental blocks as they are no longer needed. Watch out for unsupported syntax and change it if necessary. For example, replacing lateral join. And you need to update your SQL to support incremental refresh if needed. Following these steps will help you transition smoothly to using dynamic tables. Let's see how our system works now with dynamic tables in place. Here is the updated diagram of our data pipeline. Fivetran has been replaced by Streamkap. Streamkap, also using CDC to track changes in the data, uses Snowpipe Streaming to insert data into Snowflake in real time. Incremental models have been replaced by dynamic tables managed by DBT. So there is no additional scheduler because Snowflake takes care of automated refresh process. As you can see, the introduction of dynamic tables and the Streamkap tool has streamlined our data processing, providing near real-time data, synchronization, and transformation. This new setup has drastically improved our efficiency and reduced the total delay. And here are the improved key metrics. After introduction of dynamic tables, our model refresh time dropped from 15 minutes to under 5 minutes. This improvement has had a significant positive impact on our clients' operations, enhancing both staff satisfaction and operational efficiency. But why did dynamic tables work so well for us? So first, simplicity. Our overall lag reduced dramatically from 20 minutes to just 5 minutes. We did extensive testing and found that it was possible to reduce the lag even further, under 2 minutes. However, this required a trade-off between latency and cost. With dynamic tables requiring a warehouse with a 5-minute target lag, it spends most of the time suspended, which brings us to the next point. Cost effective. Our overall cost decreased by 3 times. The efficient use of resources means that the warehouse is not constantly running, which significantly reduces costs. Change from batch loads to stream inserts with Streamkap also reduce the usage and cost of warehouse. And the last but not least, short implementation time. We had our first pipeline converted and operational in just a week. The ease of integration and simplicity of the setup meant that we could quickly get up and running. Dynamic tables simplify data pipelines by automating dependency tracking, avoiding complex streams and tasks, and easily materializing query results. Monitoring is also a critical aspect of any data pipeline to ensure that everything is running smoothly and efficiently. This is a screenshot of the dynamic tables graph. It provides a visual representation of the data flows and dependencies within our pipeline. It's available directly in Snowflake UI. This graph helps us monitor the state and health of our dynamic tables, making it easier to identify and troubleshoot any issues. And here we have a screenshot of the dynamic tables activity. This dashboard provides real-time insights into the performance and activity of our dynamic tables, allowing us to track refresh rates, data volumes, and any anomalies that may occur. It's also available directly in Snowflake. So throughout our experience, we identified a few challenges because there were things that were problematic. Incremental refresh, especially when dealing with large volumes of data, is something we want. However, the SQL we use has to meet certain requirements in terms of what can be used and how it can be used, so that it is possible to run a dynamic table in incremental refresh mode. One of such requirements is to use CTEs instead of subqueries. It can be tricky to replace subqueries with CTEs, which may require some refactoring of existing SQL code. In incremental refresh mode, non-deterministic functions like current timestamp are not supported, unfortunately. This limitation requires careful consideration of the functions used in transformations. Initially, there was a maximum depth of 10 for DAX and a maximum of 10 dynamic tables that could be sourced. This limitation restricted the complexity and scale of our data pipelines. However, these limitations have since been updated. Now the DAX maximum depth is unlimited, and up to 100 dynamic tables can be sourced. This significant improvement allows for more complex and scalable data pipelines. One last challenge we encountered was that handling large volumes of data with very small warehouses might cause data spilling. This can significantly affect performance and requires careful monitoring and management to ensure that the system remains efficient, which means higher volume of data may require bigger warehouse or optimization in SQL. Due to those limitations, there are cases where custom pipelines may still be required. While dynamic tables offer significant advantages, they might not be suitable for every use case. In conclusion, dynamic tables work best as an alternative to complex ETL tools. They can be a great prototyping tool, allowing you to quickly test and iterate on data transformations. They can save significant time and money if they fit your use case. However, for more advanced use cases, custom pipelines may still be required to handle specific requirements and complexities. Thank you for your time and attention today. I hope this presentation has provided you with valuable insights. If you have any questions or would like to discuss anything further, please feel free to reach out. Thank you once again.
Thank you. Thanks, Marcin. That was really useful. Thank you. So we've got a few questions. I've got my own, but we'll start obviously with the community of viewers we have. There's a couple of similar ones, but let's start with what is the target? Why was the target lag set to 5 minutes, and can it be lower?
Yes. Yeah, the target lag was set to 5 minutes because it was acceptable near real-time performance for the business and for our clients. And the reason for that was the trade-off between the latency and cost. Since dynamic tables require the warehouse to be running, the processing time of dynamic tables is few seconds most of the time for every single dynamic table, which means that for every 5 minutes, warehouse is running only for like 1 minute. So there is a possibility to reduce the target lag, but it will mean that the warehouse will be running for more time, which increases the cost. So this is the balance, the trade-off between the latency and cost.
That makes sense. And I think just to help clarify that, Streamkap is reading the data in real time from the sources. And it will be pushed into Snowpipe Streaming and Snowflake in real time as well. There is a small delay in the time it takes for Snowflake to surface the data. We sometimes see that take 10 seconds, 20 seconds, and then the data is there. But of course, and that doesn't, as I'm not sure everyone knows, but that doesn't actually use a warehouse. So it only costs about $20 to import or ingest a terabyte of data. So the real cost here, actually, once you've got it in and the delay, is actually then do you want to use the warehouse, the Snowflake warehouse, to do the transformations to get it into that business state that you want to use it on. Okay, good. So you could reduce it, but it's just balancing up the cost of the transforms. Yeah, makes sense. We've got a few questions on cost. So comparing Fivetran and Streamkap with Snowflake. I guess I can talk a bit about the Streamkap costs. So we have a pricing page on our website. We charge by volume rather than per monthly active row, as Fivetran does, but it doesn't matter. We see, and it's quite normal, but we see about 5 million monthly active rows, or active rows in general, would be equivalent to a gigabyte of data, and we charge per gigabyte. So to give an example, list price starter, $500 a month would be 20 gigabytes per month for 100 million rows, or $850 a month for 250 million monthly active rows, which would be about 50 gigabytes of data. So we see that is about 3 times or more cheaper than Fivetran. And of course, our data is ingested in real time instead of on a schedule. And we're just comparing ourselves to this kind of, I think it's the 5 or 15 minute delay with Fivetran Business Edition, not the enterprise. Martin, can you talk about any savings you got on the Snowflake side? Obviously, there's the ingestion cost. What else is there? Or if you can elaborate, that's great.
So it's not only the cost of the Streamkap versus Fivetran, but also the additional cost that you need to cover when you are ingesting data not with Snowpipe Streaming, is that ingesting data in batches, you also need to pay not only for the solution like Fivetran, but also the cost of the warehouses that will need to process this data to insert to Snowflake. So this is the cost that basically reduced to zero since warehouse is not running anymore to ingest the data, and for the processing in dynamic tables, it is significantly lower than we had before scheduled in regular intervals.
Okay, great. Have you got a number on that? It's in just 50. I don't know, but like say 50% lower, for example.
I don't have specific numbers here. As I mentioned, the overall cost of the whole pipeline was reduced by 3 times.
Okay, sounds good. Okay, and another question is your new pipeline in dbt doing anything other than holding the definition of dynamic tables?
No, I mean it's also holding the definitions of procedures, other definitions that are required not only for this specific pipeline, but no, dbt is not scheduled by any way to interact with this pipeline other than the update of definition of dynamic tables or anything related here.
Okay, slight variation to that. I apologize if you've answered it. It says Nathan's talking about being in a similar situation, and he says one thing that's becoming a bit of a headache is our dbt models are built around large full table joins and transformations. Did you have to do a lot of restructuring in your dbt models when moving to dynamic tables?
Surprisingly, there wasn't that much restructuring in our dbt models. Lot of them was just a simple transformation from incremental models to dynamic tables. Some of them required some refactoring to meet incremental runtime requirement, but lot of those were very simple, unless you are using very complex SQL syntax. It should be pretty streamlined to convert to dynamic tables.
Okay, sounds good. We've got a question on Streamkap's data source support. Do we support Postgres, Mongo, S3, and Kafka? Yes, we support all of those, in effect. So again, visit our website. You'll see the sources and destinations we support. What is the requirement of the database in Postgres and Mongo for Streamkap to read real time from them? Actually, this is for Samuel. The changes required, you've probably already got in place. So this is just a user, some permissions, and depending on which one you're talking about there, you need to enable change streams, for example, if it's not already enabled. It doesn't take much effort at all. Again, you can visit our website and our docs. It's kind of like a 5-minute process to implement the permissions. I mean, you really can get it up and going in a test environment in, let's say half an hour to an hour, and that's being generous if you, if you just follow the docs. Okay, another question. Was there? I think it's the last one. Was there any specific partitioning required on the source table to optimize the SQL query performance feeding the dynamic table?
No, I'd say no, because what is ingested in Snowflake is CDC events. So basically, this is every single change that happens on your data, which can be converted into the most recent state of the table, but it won't affect the partition, that any specific partitioning you may have, and I don't think it will affect the performance of dynamic tables in any way.
Yeah, I'll just add to that. There's no load. There's really practically zero. There's practically zero load on the source database. We're actually reading from the log. So when we do a first backfill, we do a select statement in a clever way to backfill the data with minimal load. And then we'll switch to streaming mode, and that's reading from the log data. So it doesn't matter how much load is there. It doesn't matter which changes you make. The data will just stream through. On that note, just to finish up, there was a question on we're having problem with 5-tran upserts causing queuing in Snowflake. And you won't have any issues with that either. So Snowpipe Streaming will receive all the data in real time and be surfaced. And we've got clients with, including Spot-on, with extremely large volumes, and there's no issues at all. So it's much more efficient and faster. Okay, that's the end of the time. I think we got through all the questions. Thank you again, Martin, for joining us. Very helpful. Hope everyone else finds it useful as well. And until next time.
Thank you.
Okay, thanks a lot.